Hello everyone, welcome to GATE Pass. So in this video I am going to start problems on thermodynamics which appeared in year 2019. So the first problem which I have picked is very similar to the problem which we had taken in the last video. So similar type of problem, it came in GATE 2020 as well. So most of the background and the concepts and the equations which we have to use, we have covered in the last video, so you can go and check over there. So briefly I will describe the problem. So this is the reversible reaction which is taking place at a constant temperature of 800 Kelvin and pressure of 2 bar. Delta G0, that is the standard Gibbs free energy change of reaction, that is given, and it is further given that the reactants and products, both of them behave as ideal gases. The initial number of moles of the two reactants are given, and they have asked you to find the extent of reaction. So the problem is very similar to the one which appeared in 2020 and which we have already solved. The only thing which is different over here is that now the pressure is 2 bar. Okay, so let's see. The thing is this, that since this problem, it looks very lengthy, so you have to really make out steps in which you have to solve this problem. Okay, so the first step I will suggest is that everything for the calculation of the equilibrium constant is usually given in the problem. Okay, so you have your delta G0, R value 8.314 in SI units, and T is given as 800. So I will put everything over here, and my first step will be to calculate the value of K. Okay, so I am just writing the value directly. You can just plug these values and quickly find out what is the value of your equilibrium constant. So it comes out to be 0.0316. Okay, next we will go to this equation. So for explanation sake, I am going to write this equation again over here. So I have phi I cap yi p upon p naught, and everything is raised to nu I, that is equal to your k. K you have already calculated. Okay, now they have asked you that both reactants and products, they behave as ideal gases. So this thing goes to unity, and I am left with only yi p upon p naught. Let's separate these two terms. Okay, so yi, and I can also write p upon p naught raised to nu I. This is also raised to nu I. Okay, that is equal to k. Now let's simplify this term. Okay, so your p upon p naught. P is the pressure of the reaction which remains constant throughout the reaction, and p naught is the standard pressure which is taken as 1 bar. Okay, so p upon p naught, essentially it remains constant. The only thing which changes with this species is your nu I, that is your stoichiometric coefficient. Okay, so from maths you know that if you have like terms like this, x raised to a into x raised to b into x raised to c, something like that, when the bases are same, what you do is that you add up the powers. Similar is the case over here. I have to multiply, in which my bases are same, but only thing which is varying is the power. Okay, so I have to take this summation of the power in this case, and you all know what is summation nu I, that is we are denoting as nu. Okay, so instead of writing now this, I can write the whole thing as p upon p naught raised to nu. Okay, so I have now simplified this equation. Okay, now let's find out what is nu for this reaction. Okay, nu I have said it is addition of all the stoichiometric coefficients. For this it is minus 1, plus 1, plus 1. Okay, so I have essentially minus 1, plus 1, plus 1, that is equal to 0. So your nu value is 0, and anything which is raised to 0, its value is 1. So the only difference in the in the problem which we have taken in the last video and this video was that the pressure was given, but ultimately because of your summation of your stoichiometric coefficients, this term again turns out to be unity. Okay, so now you are left with only product of all yi raised to nu I, that is equal to k. So now we are going to use this equation. Okay, so let's now what is our third step? So first step was to calculate your value of k. Second step was to simplify this equation according to your problem statement. And now the third step is to calculate your yi in terms of your extent of reaction. Plug it in this equation, simplified equation, and find the value of extent of reaction. So that's what we are going to do. I have given you how to calculate your yi's. Now there will be 4 yi in this case because there are 4 species. So let's write all of them quickly. So y of CO, that will be equal to how much is charged? 1 mole. Stoichiometric coefficient is -1 multiplied with epsilon divided by total number of moles. So initially how many moles are there? 4 plus 1, 5. 5. Okay. And what you have is your plus nu into epsilon. But nu we have seen that it is equal to 0. Summation of all stoichiometric coefficients is 0. So it is, there is no other term of epsilon in the denominator. Okay. Similarly, I can write y of H2S. How many I am charging? 4 minus epsilon upon 5. Okay. Next, I am going to write for the products y of COS, that is equal to, initially nothing is charged, so it is epsilon upon, how much is there? It is again 5. Now y of H2, that is again epsilon upon 5. So you have written all the mole fractions in terms of your extent of reaction. Now we will put this in this equation. Product of all I, yi raised to nu I, that is equal to k. Okay. So first of all we have yCO raised to -1, yH2S raised to -1, yCOS raised to 1, yH2 raised to 1, that is equal to k. Okay. Now I am going to put the values epsilon by 5 into epsilon by 5 divided by 1 minus epsilon by 5 into 4 minus epsilon by 5, that is equal to k. Okay. Just check whether I have written everything right. Now what happens is 5 5 is a 25, 5 5 is a 25, these will get cancelled. Okay. And what you are left with is epsilon square upon 1 minus epsilon into 4 minus epsilon. Okay. So what you have now is a quadratic equation in k which you have to solve. Okay. So let's solve the value and find out the values. Okay. So if you simplify this equation, I am going to directly write it and separate the coefficients for epsilon square and your epsilon, you get this equation in terms of epsilon and k. Okay. This equation simplified, it becomes like this, and you can solve it directly, or you can use your whatever the formula which is there for solving your quadratic equation. Usually I prefer that, so I can write epsilon as minus b plus minus under root of b square. B square is 25k square minus 4ac, so minus plus 4 4s are 16, a is 1 minus k into k. Okay, and it should be divided by 2 times a, so 2 1 minus k. Now in this form, now I am going to put the value of my k. See over here, if I take a negative value, then this extent of reaction does not have any meaning because it is never negative. So I am not going to take the negative value. I will keep the positive value of this under root d. Okay, and then I will solve it. Do these calculations by putting the value of k as 0.0316, and then you will get the extent of reaction as 0.288. So this is your final answer which is given in the key. Okay, so always remember, in such type of question, go systematically. First of all calculate k, then simplify your equation according to all the assumptions which are given. Then go ahead and use this equation to find yi in terms of your extent of reaction, plug it in this equation and then solve it. Okay, so next I am going to take another problem which appeared in 2019, which was based on the entropy change of an ideal gas in a process. So the second problem is question number 3, which appeared in GATE 2019. Okay, in this case it has been given that there is a 1 mole of ideal gas at pressure Pi and temperature Ti, and it is there in a rigid and an insulated container. Okay, now there is a partition which separates it. On the other side there is vacuum. Okay, now this membrane, it ruptures and the gas expands, so that the final pressure is given as initial pressure divided by 4, that is 1/4 of the initial pressure. Now Cp, Cv, R, everything is has units of joules per mole per Kelvin, and they have asked you to calculate what is the change in the entropy. Okay, now we have all seen this in last videos, I think of 2022, where I have derived this equation for ideal gas. So the entropy change of an ideal gas, you can derive it. It comes out to be like this. Now we are going to use this equation, but before we apply this equation, we will simplify it. Okay, and let's see. So this is an ideal gas, fine, and it is a closed system. So I can write down my first law. So delta U is equal to Q plus W, where I am saying Q is the heat which goes into the system and W is the work done on the system. Okay, so that is my sign convention. Now delta U is equal to Q plus W. Since this is an insulated container, so no heat is coming or leaving the system. Okay, so essentially your Q is 0. Now when this membrane ruptures, this gas expands, but it is expanding against vacuum, so the gas is not doing any work. Okay, so the work done again is 0. So what you end up is with delta U, that is equal to 0. Okay, for an ideal gas, you know that your U is a function only of temperature. If your U is not changing, okay, delta U is equal to 0, that means your U is not changing, that means your temperature is also not changing. Okay, so your temperature is fixed, so there is no change in temperature. When there is no change in temperature, then this term which has dT in it, it goes to 0. Okay, so what I am left with is that my delta S, that is equal to minus R ln, and P by P naught. P naught is the initial pressure and P is the final pressure. Both of them are given, so I am writing it in terms of that. What is your final pressure? That is Pi by 4. And what is your initial pressure? That is Pi. Okay, so then it is minus R ln, Pi gets cancelled, 1/4, or I can take this minus sign inside and I can write R ln 4. So this is your answer. So within 1 minute you can solve this problem. Okay, so there were 4 options given in this problem. You can see that directly you can find out it is equal to R ln 4. Okay, so I have seen that there are so many problems in GATE exams which come based on the entropy change of an ideal gas. So what I will ask you is that just remember this equation. Okay, because it comes very handy. This question was only for 1 mark. So if you remember this equation, you can solve this problem within half a minute. Okay, so that's all for this video. If you like my video, please don't forget to like and subscribe to my channel, and thanks for watching.